Well, hello and welcome YouTube. You're watching Mr. Robinson's Q&A Power Hour. Here in this hour, I'm going to be answering questions asked by my students and for my students, of course, and for anyone else who is interested. This stuff, I'm blending both of my classes together, my Integrated Math 1 and Integrated Math 2. Hopefully it lasts less than an hour. We'll see how it goes. Within this bit here, Integrated Math 1 is going to go first, Integrated Math 2 is going to go second. If you want to find your specific question or specific questions that's asked, go ahead and check the timestamp in the description section below. I know my audio is being recorded. I'm watching the thing go up and down as I talk this time. I really apologize for last time having that not happen. I was really demotivated to not answer those things again. Not the questions, just do it again. Once you waste an hour doing, I don't need these headphones. Once you waste an hour doing something like that, then you feel not compelled to do it again a second time. So again, check the description section below, especially if you're in Integrated Math 2. You don't need to hear these first ones here. However, what is the Power Hour? What are we going to do here? Basically, my students asked some questions for me regarding the content that they're covering. Integrated Math 1 is covering units involving functions, function notation, continuous discrete, domain range, and sequences, specifically arithmetic sequences. So when you see questions out of them, it'll probably be in that realm. Questions are asked and answered in the order that they're received, so you might see them jump between functions and sequences use functions as well, by the way. They are testing next week, so it is important that they do get this video out. Integrated Math 2, they last just had a unit on, what was it, polynomials, where they were doing things like distribution, combining like terms, FOIL method, binomials with trinomials, different things like that. You add the exponents when you multiply the things. I don't remember seeing a question. I didn't look at these questions in great detail at all, but I don't remember seeing a question based on why do we add the exponents. So if that's not asked, I won't answer it. So like I said, questions are asked and answered in the, their current unit that they're on is quadratic functions. And so far, all they're doing is they are graphing them. They did them from the origin, and they did them out of vertex form. And both of them, I've introduced a tableless method for doing so. So if you see some questions based on the thing of quadratic functions and graphing them, we'll take a look at those as well. Again, questions are asked and answered in the order that they're received. So if you see anything that seems out of order in that realm, that's okay. Just check the description section for a different kind of question that you're trying to see asked and answered. And I hope that I cover it in great enough detail. I always hope to not go too long, but you know that I am a talker and this kind of stuff just does happen. Again, Integrated Math 1 comes first, so I'm just going to go ahead and get it started right now. And in Integrated Math 1, the very first question that we have asked here is how to construct an equation from a word problem. I didn't realize this was one of the questions on here. I'll be honest when I mention this right now. I've done this before. I'm not saying, hey guys, I've explained this before. I've answered this question before in a Q&A Power Hour video, not this year, but from previous years. And it's hard for me to answer this quickly. Every word problem's different here. So I'm trying to think of how I want to best go about answering this here, how to construct an equation. It's a brilliant question. This is something that a lot of people have trouble with. And keep in mind the different kinds of questions that we're looking at in Integrated Math 1 for word problems are really just linear functions. And what I mean by that is they come in a form that looks a little bit like, I don't want to yet say y equals mx plus b, but I will. What I mean by this is that you have some sort of dependent variable on this side. You have an independent variable on this side multiplied by some rate. And then you have this constant guy right here that often appears. So I'm going to write some of those things out. Whenever we're looking at word problems that we see right now, for the most part, we're seeing them in this form. We saw some earlier in a different, what's called standard form. I'm not going to get into those now because that's not what's being used in function notation. By the way, y and f of x are both the same thing. So if you ever see an f of x or whatever, that also works. X is your independent variable. Y is your dependent variable. And then this m, this is some sort of rate. It's going to multiply by your independent variable. So first things first, when you're constructing a word problem out of the function notation, linear equations that we're seeing here, this is often what you're going to be dealing with. And the question is, how do you construct this? So what you got to do, and I'm going to try and type some things out here as far as what you want to get done. First of all, you read the problem, right? You read the problem, and the problem generally asks a question. Even if it's not in question form, they might say, find the blah, 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 right? There's a question of what is unknown. And within that question, those unknowns are your variables. So you have to discover what you are trying to solve and identify them as variables, as your variables. I think I can bullet point this. Give me a moment. You want to identify these as your variables. What you don't know are your variables. And what I mean by that is if they tell you that you make $40 per hour doing something, then you know that number, 40. That's not a variable. In fact, that would be a rate because the $40 per hour thing, and I'll dive into that next. When they say something at the end like find the amount of hours or find the total amount of dollars worked after so many hours, whatever, those are variables. Find the, or what are the number of hours you'd have to work for to make whatever. Those are the variables because those are things that you don't know that will change, and you have to determine which one's independent and dependent. So identify them as your independent and dependent variables. Okay. Now, we've talked about independent, dependent. Someone might have a question on this still, but what about independent versus dependent here? Independent is the one that's freewheeling and choosing. Normally, it's often a time basis. If there's time, normally that's independent. But independent's one where the independent determines something for the dependent, right? The dependent, if I say, how much money will I make? The question often first is, how long did I work? Right? Obviously, there's another question, how much do I make per hour? But that's already probably given. So, hey, how much money will I make today? That depends. How long did I work? That means the length is the independent there because how much you make depends on how many hours you work. Right? So there's that kind of thing. And some people say how many hours I work depends on how much money I make, if you know what I'm saying. But the hours can vary. We're not looking at a set amount of hours yet. Once something's substituted, it depends the other. It determines the other thing. There's more to that I would talk about that's really important for this, really, and it has to do with unit alignment. I don't know if I can get into it here. I haven't really talked about it in class, so I don't know if I'll get into it here. I kind of want to. I will talk about it, but you won't know when I brought it up. It has to do with agreeing, your units agreeing when you do something. Anyway, I got to keep moving on with this. Discover those as your variables, your x and y, your x and your f of x, or your q and your f of q, whatever you want to call it. Okay, the next thing is identify your parameters. Now, what a parameter is, in this case, I'm looking at that m and that b, m and b. Parameters are numbers that they fixate for you to use, meaning that $40 per hour, that would be something like m. That would be your rate of something, right? Per. When you see that word per, let's see, m being the rate is often identified or recognized, is often recognized with per or every or let's see. I'll just use that for now. With per or every, right? If I make $4 every hour, right? That's another per. Or if they say the word rate, literally if they say the word rate, that's how we're going to recognize that thing. Because it doesn't mean $40, right? If I make $40 per hour, did I make $40? Only if I worked 1 hour. But if I worked 10 hours, guys, that's $400. So that is a rate. Okay, that's a rate that gets multiplied by the number of hours, and then you get that amount. Okay, so it's often recognized per every. B, this is a constant. This is, I don't want to just call it a starting value, but it often is an upfront thing that you're looking at. B is an item unaffected by your independent variable. What I mean by that is no matter how your independent variable changes, your B will remain unaffected when you're building that out. So if it's something like my money thing, right? I already have $3,000 and I make $40 per hour. Okay, those are my two parameters. The 3,000 is that constant. No matter how much money I make with the $40 per hour thing involved, no matter how many hours I work, will not change the $3,000 that I already have. That is a constant. You can call it an upfront amount that I already had it. You can call it a starting value. These things occur, and I'm obviously using a lot of things with money and time right now. Remember the taxi cab fare problems that we've done before where you get into a taxi and there's going to be a $5 charge added on top of the amount of miles that you drive and the cost per mile driven. I guess that's not hours, that's miles. Or something like there's a shipping cost. There's a shipping cost to an order, and you pay $5 per item for a certain number of items. The items you don't know, but that's an independent variable, and that depends on how much you spend. But that shipping cost doesn't change no matter how many items you order, right? If I order 1 or 1,000, the shipping cost is the same. And that's not true everywhere, but these word problems, they're doing that like a flat. They say flat rate. Sometimes they say the word rate, but if they say flat rate, fixed rate, something like that, that means that is not going to change with your variable. So you'll see something with B in that realm as well. I wish I could do word problems for you. Like I just made some up right now. So let me talk about one of those that I did. Let me do one more. Let's say it's a babysitting thing. Okay, so you're a babysitter. I'm not going to type it out, but you're a babysitter and you charge, $10 per hour. I don't know how much they charge. They charge $10 per hour, but because of reasons such as convenience, time, making sure that they kind of make it worth your while to do it, maybe you also include something like an $8 upfront cost, meaning they're going to pay you an extra $8 on top of it. It's gas money. It's time out of my day. I could have been doing something else. This is just a little, convenience fee. You see those on things like StubHub and stuff like that. Okay, the per hour here, this is your rate. Your rate gets multiplied by the number of hours that you work. It gets multiplied by the number of hours you work, and then that becomes a dollar amount. You'll say, this was a dollar amount. No, this was a dollar per hour amount. You multiply by time, your number of hours there, that's when you get dollars. So your dependent and independent are both variables, right? What is the independent variable here? It's the number of hours that you work. So if I use that as x, I'm going to say x is number of hours. And then f of x, which by the way depends on number of hours, f of x or y, that's the amount of money made. Total money made. So when I make an equation like this, and this is kind of where I'm going to stop here because I got to go to the next question. When I go to the money I make here, or excuse me, the equation that I do, my money I make is a function of the number of hours that I work. The money that I make is determined by, I'm going to start with the 8 thing. The $8 in upfront cost and says no matter how many hours I work, you'll still be adding $8 to me working. This assumes you work at all. I guess 0 hours worked, maybe they don't pay you unless you go there. See, this might happen. Realistically, you go there and they say, never mind, we have to cancel, we got to stay home, or, we're going to stay home, we don't need you anymore. Here is money for your troubles. Here's some money for your troubles, right? Because that's what you're adding in each time. Never worked an hour. Boom, still made $8. Oh well. Maybe you canceled your plans too, and that's really inconvenient. You say that's going to cost you. All right, I'm getting off track. So $10 per hour here. We don't just do 10 plus 8. You don't just make $18, not unless you only work 1 hour. We don't know how many hours we work. That's why we use that x. 10x plus 8 kind of gives you that there. Now, this is the part that I said I wouldn't talk about before, and I kind of will now. Remember how I was talking about unit agreements here? 8 is in dollars. 8 is in dollars. This is $10 per hour. Dollars per hour. Per is a division. And you multiply that by the number of hours worked. Hours divided by hours cancel right here. 10x is also money. You're adding money with money. You know what comes out as a result? Money. Why? Money. Now, why am I bringing that up? Because if you wanted to say that you wanted, because if you're not sure which one's independent, which one's dependent, hours versus money, does it make sense? Sense like money. Does it make sense for me to put hours here and then dollars per hour times dollars here? And hours won't cancel anymore, right? Now it's dollars squared per hour plus dollars equals hours. There's a unit disagreement and mismatch there. Those units don't align, and this is something that wouldn't make much sense to you other than the idea that money plus money should equal money. You can't do something like pizza plus socks equals pounds, right? You can't put things that are where the numbers don't align together. You can do dollars plus cents equals something. I can't say $3 plus 2 cents equals 5 somethings, right? It equals $3.02, but that's because 2 cents is $0.02. So you change this into a different unit agreement, right? You can only do things that agree here. Now, when you say $3.02, you really mean $3.02. So that's the idea. You need unit agreement when you do those. And that's something I don't speak of enough. That's something I've spoken of too much here. I did say this one would take a while, but as the question was asked, that's how your setup kind of works. Figure out your variables. Identify your parameters, independent, dependent. Identify your parameters. One's a rate, one's a fixed amount. Sometimes they don't have a fixed amount. And you kind of write it in that form thereafter. And we use it to solve questions that are asked. Okay, I hope that did cover it because I do want to move on. The power hour is already a quarter of the way through. All right, next question is, what does it mean when the math book says find the 10th term of the sequence, and how do you do it? Okay, so this goes to our newest chapter and module that we're doing in sequences. So let me kind of clear this out and talk about what they're saying there. And remember, this might go out of order. In other words, there might be a question that leads up to this kind of question that might be answered. So whenever you have a sequence, and I'm just going to write a list of numbers here that follow an arithmetic pattern. If I had the list here, 2, 5, 8, 11, 14, 17, 20, 23, 26, and 29. Now, this is going to keep going. Now, the question that was asked here first was, what does it mean when the math book says find the 10th term of the sequence? So, first of all, they're not going to write a list this large. I'm just expanding this in this way. This is the first term. Now, notice that the number is 2. The value of the term is 2, but implied that is the first term right there. There's a little 1 that I'm writing. This is the second term, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th. And the 10th term right here is 29. So when they ask find the 10th term here, they do mean that in this list, if you kept expanding to the 10th term, we're looking for that guy there. Now, they don't often ask you it in this way. That being said, even if they truncated the list to only 4 items right here, and they ask you to find the 10th term, it is conceivable that you could find this 10th term just by determining, if this is an arithmetic sequence, that's kind of what we're working on right now. Although they ask it in different ways, but since we're building arithmetic sequences, I wanted to show you this. Because you might recognize, guys, there's a constant pattern when I built this list that 3 is added every single time here. You could work in this recursive format, which means use the previous value to find the next value. And I could find out, hey, the 5th term, that 5th term, guys, is 14. And that 6th term is 17. And the 7th term is 20. And the 8th term is 23, and the 9th term is 26, and the 10th term is 29. So you could keep going and find it that way. It's logical, it's conceivable, it's not too far-fetched. They're really easy numbers to add. It's pretty close to 4. 10 is really close to 4, so it's not too many you add. Now, if you wanted to do that for the 100th term, not necessarily looking to do that here. To limit the answer in this question to just the scope of what people are asking those, what does it mean to find the 10th term and how do you do it? What's often going to be done instead of being given this sequence or given something that you know for sure is arithmetic, and I'll give you a different kind of example, is if you're given an explicit rule. Now, I'm not going to dig because I'm seeing down below what is the difference between explicit rule. I'm going to talk about explicit rules later as far as its meaning, but here's an example of an explicit rule. I'm going to do one a little bit different here. 2n squared minus 7. Okay, what if this is your explicit rule right here and they say find the value of the 10th term? Okay, what we do in an explicit rule, I guess I do have to kind of explain what an explicit rule is to tell you how we're going to do this. An explicit rule means that n represents the term position. Remember when I wrote 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on top of those numbers? Those are my n values. That's the position of the term. 2 was in the first position or first place. 5 was the second term. 29 was the 10th term. Those n's, those numbers were the n values. Those are term positions. So when we do an explicit rule, we actually plug in the position right here. If I want to find the 10th term, I'm going to plug 10 into here. And it will actually tell us what the value is going to be. This rule defines it as such. So to find the value of the first term, just to, you guys will be asked, write the first 4 terms, stuff like that. To find the value of the first term, you substitute 1 in for n, like this. And I'm only emphasizing this because to show you order of operations. 1 squared is 1. 1 times 2 is 2. 2 minus 7 is negative 5. So your first term in your sequence is a negative 5. You could find out the second term, the third term, and heck, you could find out the 10th term. So to find the 10th term here, what does it mean when it says it? You saw the list. It means find the 10th term that appears in the sequence. How do you do it? If there's an explicit rule such as this one, you substitute 10 in for n. N is the position, and 10 is the position in this case here, and you calculate. F of 10 means the value of the term. The last time we saw it, it was 29. This time, it's going to be something way higher. 10 squared is 100. 2 times 100 is 200. 200 minus 7 is 193. So the 10th term in this sequence, where the first term was negative 5, the second term would have been 0481. The third term would have been 11. This is not arithmetic, by the way. This does not have a common difference. You would have kept going, bum, 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 bum. 10th term would have been 193. So 10th term means in a sequence, in a list, it's the 10th number. How do you find it? In an explicit rule, you substitute it into there. You could do it recursively if you recognize the recursive pattern from one value to the next. You've only seen it really for arithmetic sequences with a common difference. And you'll only work recursively that way for now because we're not doing recursive rules. Other than that, guys, work the explicit rule, plug in your number, and go. All right, with that question down, let's go on to the next question. And the next question asks here, what does it mean? When are we going back to school? Okay, and I think they mean in the physical realm, not like, hey, I'll see you Monday on Zoom. So the current form, and by the way, whoever asked this question, keep this in mind. This is not a content-based question. It's a curriculum-based question. It's not even curriculum-based. It's students get credit for asking questions for these things. This student who's asking, pique your interest, this doesn't give you credit for it, right? You have to ask a math content-based question over the course of the last 2 weeks that were covered. So next 2 weeks, guys, when I make another Q&A Power Hour video, make sure that you ask me another content-based question. Or you might have down here, I don't know. Okay, when are we going back to school? So this current district is formulating a plan so that going next semester, starting January 5th, which is my little sister Kelly's birthday, by the way. She's turning, I don't know how old now, born in 94, 20, 21. 27 years old. Jeez, time flies. She's my baby still. Anyway, January 5th, 2020, starting next semester, they're planning a hybrid model. Now, the hybrid model, I don't have the email here written out. I think they sent it to parents and the entire community. The hybrid model is where part of the people are at home, part of the people are in school, the teacher's at school, and is Zooming while doing things in the classroom with some of the people there, and then some of the people are at home. Benefits range from different things. I don't know all of them fully. I wish I could tell you. I think there are a lot more drawbacks than there are benefits, specifically from my end, how I'm going to make things work, turn in homework, do things like that. But one of them, sometimes the kids just need to be in school. Sometimes some students can only afford to be there. Maybe their internet, something. I'm not going to talk to the benefits, but anyway, the hybrid model says that some people will be there, some people not. You're always going to have one instance, it seems like, where you are doing some distance learning as a student. That means they would put them down in like 3 groups here. And I didn't read this in full, and I didn't read it a second time. What I saw when I skimmed it was there are 3 groups: Group A, Group B, and Group C. Now, to make this easy, Group C is only distance learning. I'm going to put DL, stays at home. Group C is specifically distance learning. I don't know how this is determined. I don't know if you fill it out and decide for yourself. I have no idea. But Group C only stays at home and does the Zoom only. A and B are the hybrid portion and we're going to stay on the same bell schedule. So what that means is Monday, Thursday is 0, 1, 2, 3. Tuesday, Thursday is 0, 4, 5, 6. If you have 0, I teach 0. You see 0 every day. And Wednesday is short day. Now, the other part to make this easy, Wednesday is only distance learning as well. I assume it's still the short day format. Teachers have meetings after school. I host office hours, etc., etc. Now, I don't know how the A and B work. I'm just going to pretend that I do know. Let's say that we're doing the whole Monday, Tuesday, Wednesday, Friday thing. Well, A will go to school. We'll go to school maybe on Monday, and let's say they go on Tuesday. I'm not sure. Let's say they go to school Monday, Tuesday. That means B will be distance learning on Monday and Tuesday. That means that A goes to school for their full classes, B stays at home for their full classes. And then on Thursday, Friday, A maybe does the distance learning, and then B goes to school Thursday, Friday. So it's something like that. That's what it sounded like it said. Again, I didn't read it twice. This may be way wrong. Now, you just asked when we're going back to school. The answer is kind of depending on what you're doing. The official answer is January 5th. That is the plan. Who knows what's going to happen? That is the plan. I'm not looking too forward to this. I'll let you know right now. That's not me speaking against anyone or anything here. I can't wait till we can all safely go back to school in full as if it was this past February. I can't wait for that. This thing, I have some trepidations about. It's a little scary for me. So we'll see how that thing works. But there we go. I hope that answers that question. Okay, the next question down, and this goes back to the sequences we're talking about. What is the difference between explicit rule, specific term, and recursive rule? Okay, so maybe you're just asking me to define all 3. Now, if you just ask what's the difference between explicit and recursive, I can answer that better. Specific term is not a mutually exclusive item. It's not really, it's related to them, but it's not one or the other or something. It's something that's within. It's like saying, what's the difference between heads, tails, and a quarter? Right? The quarter might flip the coin present, like that. So anyway, let's talk about explicit versus recursive. Now, the words, you do want to understand a bit of the words because I use them. I use them. I do want you to know that we are not using recursive formula, although we use recursive logic. Let me kind of type out what the two things mean and how they are explored. I mentioned explicit before, but let's say it again. An explicit rule is an equation such that you can find the value of your term, meaning like the value of the 10th term was 29 or 193 or whatever it was. The value of the term can be found by using the term's position, meaning if I want to find the value of the 10th term, 10 is actually used in my equation to find it. I actually substitute the number 10. And that uses that n idea there. That uses the n idea where you substitute n 10 for that, for example. That's explicit. Recursive, and I promise not to get into the equation for it. By the way, with explicit, I'm also going to write the formula for you guys. I don't think there's a question on the formula. So recursive, whoops, that was a copy paste. Recursive means you find the value of the term by the value of the previous term, meaning you bank on the value of the previous term to find the value of your next term, okay? So in other words, this is when I say recursive logic. If you guys remember that one list that I mentioned here, if our list starts with 2, 5, 8, and 11, and say I ask you to find the value of a specific term, I'm going to tie this all together. Remember when this thing said specific term over there? When I want to find the value of a specific term, let's say it's the 10th term. I can do that recursively by following the pattern from one number to the next. And once again, as an arithmetic sequence here, we are adding 3 each time. I'm doing exactly what I did last time, just rehashing. If I want to find the 10th term, guys, I have to first know what the 9th term is, because I got to add 3 from the 9th term to do that. If I want to find the value of the 9th term, I got to know the 8th term. 8th term needs 7, 7 needs 6, 6 needs 5, 5 needs 4. So to find the value of the 10th term recursively, I got to first know the value of the 4th term. I got to add 3 to it. Recursively, so this is what recursion is here. Recursion means kind of like looping through something over and over, kind of reiterating a process and going back into it, pulling out a new value from the value that you previously had. So 11 was the previous value. What's the new value? 14. Add 3. What's the new value of that? After add 3. 17. That's the 6th term. Specifically, the 7th term is 20, 8th term is 23, 9th term is 26, 10th term is 29. That's how I built this sequence for the first time, by the way, guys. I recursively just kept adding 3. There are benefits to it to find next terms immediately. It's pretty straightforward. This is how we tend to think a lot, especially when you see a pattern, right? If I say to you guys, hey, what's the pattern here? A lot of people will just say add 3. They wouldn't say something like, you start from this number and you multiply by 3, you add 3 a certain number of times and blah, 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 because that's what an explicit rule will be. I'll even give you the explicit rule for this one, this specific one, as well as give you the example. An explicit rule actually uses n, you know how this is 10? This would be n in this case. It actually uses the 10 to calculate it. So here's the explicit formula, by the way, and I'm going to use function notation, not subscript. But function notation says to find the value of some term, you take the value of your first term, and you add your common difference n minus 1 times. Now I do believe, and I was going to do it as the head of the thing here, I do believe someone asks why is this formula what it is, so I'm going to save that question. But here is the formula. F of 1 means the value of your first term. In this particular case, my value of my first term was 2. So F of 1 is going to be 2. D is the common difference. This is for arithmetic sequences, by the way, guys, this formula. D is the common difference here, which is 3. 3 is added each time. That means 3 is the thing that goes right here. N is the term that we'd be looking for specifically. So when you guys ask specific term, that's specifically what's the value of some term. You plug in that position in here, and that will equal the value of whatever term you're looking for. So here's the formula for it. These things can be simplified. I gotta make haste with these guys. So this can be simplified. I'm going to distribute. So f of n becomes 2 plus 3n minus 3 distributed, and combining like terms, 2 minus 3 is negative 1. So if you want to write it simplified like that, that's pretty helpful. You'll see a lot of explicit rules put in this way. So that is the actual form for this thing here. I'm not going to give you the recursive formula. It basically says use the previous term, add your common difference, and it says start from some number. It's a weird looking formula. We're not going to use it. You know how to do this logically. Explicitly, it makes more sense to see the rule. And when you see the rule, what's nice about explicit formulas is I can find the value of any term imaginable that I want off the drop of a hat. Just plug it in, calculate. I don't have to add 3 a bunch of times to do it. If I want to find the 1,000th term recursively, that's going to take a long time. If I want to find it explicitly, I plug in 1,000 specifically. But what if I want to find the value of the 10th term? Just like I said last time, I substitute 10 in for here. 3 times 10 is 30, minus 1 is 29. Just like this one showed, that's finding the value of a specific term when asked upon. You substitute the number of the position inside for n when you're given the rule or when you find the rule, and then you use it to calculate the specific value. So recursively, you can find specific term here, term's value. Explicitly, you can find it by substitution, find the specific value. Both of them work. This is for arithmetic sequences. That's what we're working on. And I hope that answers your question. All right, with that one down, I'm halfway through the power hour here, and I've only done 4 questions. I know some questions go a little faster than others. This next question says, what is the difference between continuous and discrete? Now, continuous versus discrete was more of a chapter 3 conceit, the previous chapter before this one. Chapter 4 on sequences is only with discrete functions because there's only a first term, a second term. Let me get into that in a second. The easy way to talk about continuous versus discrete on a graph, here's going to be, let me copy paste this guy and kind of make him thinner. Copy paste. So continuous means basically that your dots are connected, that there is this ebb and flow, continuous, there's ebb and flow to all of your points in your domain and range, that I don't lift my pencil from the paper when drawing the graph. It does not just mean there's a straight line. It does not necessarily mean that it goes on forever, and it doesn't absolutely mean that it's always a function. It just means that all your dots, if you plotted points to kind of get yourself started and connected the dots are together there. How do you identify between when you do continuous versus discrete? It depends on the logic of the situation. Because continuous here means that no number between whatever and whatever is skipped. Let me actually just start it at 0 to use a real world context here. Let's say that you're selling tickets for something and this is profit or whatever it is. I can't sell half of a ticket. So when you're looking at 1, 2, 3, things like that, this can't be a model for tickets and profit or anything like that. This would be a weird model for profit, but this can't be a model for tickets because this point exists on your continuous curve, which is 0.5, and you can't sell half a ticket. So continuous is only used in certain situations such as time. After an hour this, 2 hours this, 3 hours this, but I can track half an hour when, say, maybe there's temperature or something like that. 0.5 hours, I can track that bit. That's why continuous, I connect the dots maybe, or I do for continuous, but that's why in time bases, I connect the dots because I can track things between those points. Discrete, on the other hand, discrete, you don't connect your dots. They are fine, very specific values here that you plot. You get point. They're not connected. There's considerable space in between them. You could write them as a list in your domain and range. This could be at 1 hour, 2 hours, 3, or 1 ticket sold, 2 tickets sold, whatever you're talking about. I won't get too deep in the word problems. Our sequences that we do, guys, are all discrete. Their domain actually starts at 1. There's not even a 0 here to continue. If you graph a sequence, they will always be discrete. You do not connect the dots. The word problems that you see, go and check out the word problems in section 4.3. If you're an IM1, go to section 4.3, read the word problems. All of them should, if they do it right, because they're sequences, all of them should have this conceit that they should be discrete based on the information. Selling a number of tickets, doing, I can't think of situations right now. But discrete means the dots are not connected. When we write these domains for these guys, let's say that this, I'm only going to say domain, range is just the Y version. Let's say this ended right here at 10. Your domain on X would be written from 0 to 10 in this particular instance right here. A domain for something like this that just does 1, 2, 3, 4, 5, for discrete, you write it as a list. 1, 2, 3, 4, 5, because there are no numbers in between. Here, you pass every number from 0 to 10, including 0.5, including 7.1, things like that. So you write it as an inequality here. Here you write it as a list. That's the difference between continuous and discrete when it comes to graphs, domain range lists, and what kind of word problems you see them in. Okay, thank you for the question, and that'll go done. Let's see, there are several more questions here. Power hour might be more than an hour here. I sure hope I have enough room here. All right, next question is, if they don't give you 4 terms for a problem, does that mean you still just use 4 terms? Oh boy, I don't know what you're asking. I know this sounds like sequences because there are a lot of times you guys are seeing sequences that say, hey, here's your list. I'll go back to this list again. Here's your list, da 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 da. Now the question says if they don't give you 4 terms for a problem, does that mean you still just use 4 terms? So if they don't give you these, maybe they're asking if they give you the sequence equation, the arithmetic. So what was this? 3n minus 1? If they give you just 3n minus 1 here, does that mean you still just use 4 terms? Maybe they're asking, do you only restrict the domain to this? So the different kinds of problems that we've seen here, even with these equations, it doesn't matter if it's arithmetic or otherwise, but in these equations, a lot of times they say find the first 4 terms. Honestly, the reason why we're asking you to find the first 4 terms is so that you're practicing using function notation and understanding things of sequences. We don't want to go too long. We want to make sure you're getting your pattern in. You understand the sequence does it. There are more than 4 terms in most of these sequences here. Remember, your domain for these things, n, can go on. Whoops, I shouldn't say n here. But n is your variable for your domain. So your domain, your input, n can be 1. It starts at 1, 1, 2, 3, 4, but it could keep going. It could go to 1,000. It could go to infinity. So when they say write the first 4 terms, that doesn't necessarily mean it stops at those 4. If they ask you for it, that's great. But they could also say find the value of the 10th term, find the value of the 37th term, things like that, and it keeps going. I don't know if I'm answering the question because I don't know what the question's asking. You find the first 4 terms if that's what they ask for, even if they only give you the equation. They often give you 4 terms, guys, because if they only gave you, look, if I only gave you, and this isn't a good example for me to talk about, but let's say I gave you this as your sequence right here. Okay, and I said find the next 3 terms for me. This one's a little weird because the next 3 terms could be 6, 8, 10, because you could be adding 2 each time. Maybe this is not an arithmetic sequence. Maybe it's something called a geometric sequence, and maybe the next terms are 8, 16, 32. You notice what's happening there? Multiplying by 2 each time. Maybe it's, anyway, you can do a lot of different things with those. So they give you multiple numbers to have you fill out the pattern and say, what is actually happening? Once you get 3 or more numbers there, like 4, you start to sense a pattern. Anyway, I don't know if I answered your question there. Your domain can be infinite, and they can ask you for terms beyond the first 4. It just depends on the problem. It depends on the problem. So anyway, this one, I don't even know what this is. 120, 111, 110. 110 right there. 37th term in that list is 110. All right. Anyway, let's keep going here. All right, the next question asks, when we graph, how do we know to put a line through it, and when do you not know? Okay, this goes back to the continuous discrete question that was asked before. You put a line through it or a curve through it when it's continuous. So you saw the continuous. You'd have to go back, whoever is asking this question, go back to the question that asks about what is the difference between continuous and discrete. Look at that, and I draw the graphs there. Now, when do you know? You know when it's continuous. The question of when do you know whether it's continuous, it depends on, especially a word problem, it depends on kind of the ebb and flow of, can we have an unlimited domain, an infinitesimal domain when it comes to the numbers? Can I have half of whatever I'm talking about? Can I sell half a ticket? No. Can I have half of an hour? Yeah, probably. So you're probably looking at continuous with time, but not continuous with number of items that you sell or buy or do something with. So you connect when it's continuous. You do not connect when it's discrete. All sequences are discrete, so you never connect when it's a sequence. All of those are that. Okay, I don't know if that answered that, but that's, saving time there. All right, next question. How do you find the position of a given term? Now, this is a different question, and I'm glad someone asked this. This is a different question than the question for how do you find a specific term, because when they say how do you find a specific term, they're asking how do you find the value of that term. They're asking how do you find the position. If you guys remember, the position is that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The values were the 2, 5, 8, 11, 14, 17, whatever. They're asking how do you find the position if you're given a value. So let's go back to the one that I keep using here. I keep using this guy, 2, 5, 11, or 2, 5, 8, 11, excuse me. Now, what if I asked you, find the position, or, not find the position. Let's see, how do you ask these questions again? What term has a value of, say, 320? Now, if I did this right, this should be a good integer number. What term has a value of 320? Or what term... Yeah, this is fine. What term has a value of 320? Now, I never said the word position here. But this time when they're asking what term has a value of 320, that means 320 is part of the list, meaning dot, 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 somewhere we're going to hit 320. And then if we keep adding 3, it's going to be 323, stuff like that. So how do you find the position of a given term? You can either do it recursively, which means you got to keep adding 3. And not only do you got to keep adding 3 and figure out what the next number is to add the next one, but you also got to count on your hand or tally up what term you're at. Oh, 14 is the 5th term, 17 is the 6th term, 20 is the 7th term, and you keep going until you hit 320. And that's going to take a while depending on what's asked. If I asked what term has a value of 14, well, it's the 5th term. You just add it again, and that's the 5th term there. That answer would be 5, you know what I mean? But we're asking, what is the term, what position gets the term of value 320 right here? Okay, that's what's being asked. So here, you're finding n. So recursively, you keep adding 3 until you find out what number it lands on. Explicitly, you want your formula. So hopefully you can create it now that you've done section 4.2. You use your formula. I think it was 3n minus 1. And before, you guys, when we would find, the value of the 10th term, we would substitute 10 for n because that's the position. Now we're trying to find the position. Now we're trying to find n, which means we substitute for f of n. All of f of n gets replaced by our value, in which case here is 320. F of some term, some n that we're trying to find is 320. What is that n that gives us it? You substitute for f of n. This is how you do it. You substitute for f of n and you solve. Add 1 to both sides. Divide both sides by 3. That's going to be 107. You can use a calculator, but n equals 107. That means the 107th term, the 107th term is 320. The 108th term is 323, etc. Explicitly, we found that pretty quickly, provided that you determine your rule. And you remember how we found this rule? If don't, go back up and find the question, how do we find an explicit rule? All right, guys, with that one down, let's go on to the next question, as I probably should have split up the power hour to 2 different IM2 and IM1 different things. I think IM2 only has five questions here. All right, next question. I didn't see these. Next question. What's your favorite actor that played Batman? Now, once again, you will not receive credit for asking this question here. I'll go and answer for you. But I don't know how you're asking it. If you're asking, hey, among the actors, just actors, and that happen to play Batman, who's your favorite of the actors? And the actors we got to think of are Adam West, Michael Keaton, Val Kilmer, Christian Bale, Ben Affleck. Heck, you could do... Who's the voice actor for Batman? Kevin Conroy, right? I don't know if that counts as playing him. He was the voice actor for the video games as well. When it comes to actors alone, listen, Christian Bale's my favorite actor. He's my favorite actor. Therefore, it's... and who's coming up? Robert Pattinson. I don't know if that counts yet. Actor-wise, I can give a lot of credit to Robert. Look, all these guys are really good actors. Michael Keaton, standout actor. Val Kilmer's good. He's not great. Also wasn't great. Oh, George Clooney. George Clooney's a fantastic actor, right? Batman and Robin wasn't a fantastic movie, though. I mean, I'm not going to rank him for you guys. Christian Bale is my number one favorite actor. Forget Batman. In fact, I don't love him in the Batman movies, if you know what I mean. I don't love him as Batman. So if your question instead was, who was your favorite Batman portrayal? Now that goes in 2 different ways, because you also could be asking when he's in the Batman costume or when he's Bruce Wayne. I feel like you would have asked if it was Bruce Wayne there. Because I like Christian Bale as Bruce Wayne. I thought he was a really good Bruce Wayne there. Ben Affleck was an awesome Batman. I loved the voice modulator. I liked his outfit. I liked his costume pretty well. And the action sequences really helped sell things, you know? Maybe it wasn't always him doing the stunts, I don't know, but he was very bulk. He had the physique of the seasoned Batman that really worked well. So Ben Affleck's a great one of mine as well. I mean, Adam West, like, hey, they're old chum. I'm not going to talk about those guys too much. Kevin Conroy's got a great voice. I can't give that away. Christian Bale, where's the trigger? You wouldn't give it to an audience. It's like, oh my God. Drink my water. I'm not going to talk on this one too much any longer. My favorite of the Batman movies is The Dark Knight. I don't know how he does that. Give credit, only good actors can do that. My favorite Batman movie is The Dark Knight. And it's not by far. There are other ones are very good. This Robert Pattinson one, I'm very excited to check out. For those who just see Robert Pattinson as the guy who appeared in The Goblet of Fire, Harry Potter and the Goblet of Fire, and the Twilight Saga, try and expand beyond your horizons. He has done some incredible indie flicks since then. The Lighthouse, and I mean, he has been an incredible actor in them. Some of these movies are going to be hard for you guys to watch. The Lighthouse, you guys won't enjoy it. Incredible acting in that. Good Time. Now, it's an R-rated flick, but Good Time. Very intense movie. I think by the Safdie brothers, who also did that recent Adam Sandler movie, Uncut Gems. So Robert Pattinson in that, you wouldn't even know it's Robert Pattinson. If you didn't know he was in it, you wouldn't have known he was in it. You know what I mean? If no one told you before it was him, you wouldn't have even known it was him. He's completely transformed. Is very good. It would sell you on this guy could do a detective Batman. Not like that character, but his acting. This guy can do certain things. Check out Tenet. He's in Tenet. He's not fantastic in Tenet, but he's my favorite character in Tenet for sure. I love what he does there. Has some fun. All right, guys, that's not math based. I gotta kind of get off that. It's just I love Batman and Batman things. Thank you for asking the question though. All right, on number 3 and 4. 3 and 4 of what? What? Hold on. On number 3 on 4. Oh, on 4.1. Sorry, I thought that was a period like the end of a sentence. On number 3 on 4.1, can you example more? What do you do to find the first 4 terms of the sequence? Define the given rule. F of 1 equals 65,536. F of n equals the square root of f of n minus 1. Okay. I'm not going to answer that in the greatest detail. This is an example of a recursive rule. These are the ones we are not doing. What I will tell you... Oh. Okay. I'll just say this out loud for the person who's asking it. What I will tell you is that it's telling you that the first term is 65,536. And then they're telling you to find the value of the next term, take the square root of the term before it. Meaning to find the value of term 2, take the square root of 65,536. Honestly, I don't even know if that's a whole number. I'm going to see if it is. To find the value of term 2, take the square root of 65,536. To find term 3, take the square root of whatever term 2's value is. To find term 4, take the square root of that one. 65,536 square root. Oh, that's not a square root button. Get off of that. What's square root? Oh, it's 256. Okay. So here, okay, I'll write this out. So again, you're not being asked to do, I'm not asking you to do recursive form, but they say the first term is 65,536. You want to know the second term? Take the square root of this. So this, I probably shouldn't put a comma there, but this, the next term is 256. I know the square root of that. The next term, take the square root of 256. That's 16. And the square root of that is 4. So that's the first 4 terms of that sequence. Take the square root of the term before it, starting from here. If you understand that within that rule, how it's being stated, awesome. If you don't worry about it. That's why I skipped those problems in the homework. That's why you weren't doing those problems. You can check my solution guide video for it as well. But that's what that means. By the way, the recursive rule is probably better to situate than the explicit rule. I don't know how to write the explicit rule for this off the top of my head. I'd have to work really hard in figuring that out. It's kind of hard sometimes. Sometimes recursive rules are required, but not for arithmetic sequences, which is what we're working on. Later, we'll do geometric sequences, also not required to do recursive rules. Okay, and the last question for IM1, which would probably take care of an hour for the power hour here, almost, is why does the rule f of n equals f of 1 plus d times n minus 1 work? Meaning, I gave you guys the formula. Why can we just trust it? Why is it allowed to be used? You know what? What's the basis behind creating that? So let me write that one more time here. And we'll use the example that I've been using a lot before to make sense of it here. Now, I did explain this a little bit in 3rd and 4th period. I didn't have time to explain it in 5th period when we did it, but some people were absent and they didn't get to hear this anyway. So they're like, what do we do? All right, f of n, once again, this is the value of your nth term, whatever term we're referring to, value of nth term. F of 1 is the value of your first term. D is your common difference. Excuse me. And n is the term is the position of term n. I'll just put term's position. Remember, 10th term, n is 10, stuff like that. All right, let's look at the list we've been doing before. 2, 5, 8, 11, 14, 17, 20, 23, 26, 29. First 10 terms of this list. I'll even give you the formula for this. Let's look at how the formula works with the sequence to get what we want. The formula was, before we simplified it, it was 2 plus 3 times the quantity n minus 1. 2 is the first term. 3 is the common difference, plus 3 plus 3. That's what we're doing here. Okay, why does this formula work? What is it saying in logical sense that we can work it out? What people really have trouble with is this part here, and you still might after I explain it. Okay, let's think about it in terms of plugging in things for n. We know what the terms are. They're spelled out. What if I asked you to find the value of the first term in your equation? We know it's 2. What if I asked you to find the value of the first term in your equation? F of 1 equals 2 plus 3 times 1 minus 1. What happens here is you start from 2, your first term. You start from 2, and you add 3 0 times. Remember, when I say 0, that's because this was 1 minus 1. You add 3 0 times. Starting from 2, you do not add 3 at all. Second term. Start from 2, and you add 3 once. Why did I say once? Because n is 2. 2 minus 1 is 1. Starting from 2, you're going to add 3 just once to get the value of your second term. Third term. Starting from 2, you're going to add 3 twice. 3 minus 2. Remember, f of 3, 3 minus 1. I'm not going to keep saying that over and over. I'm just click in it now. You're going to add 3 twice, starting from 2. To get the value of the third term, I'm going to start from my first term, 2. I'm going to add 3 once, twice. Fourth term, starting from 2, you're going to add 3 3 times. Term number 4, add 3 times. Term number 5, add 3 4 times. Term number 6, add 3 5 times. Term number 7, add 3 6 times. You see what's happening here, guys, is because we start at the first term and we're finding a specific term value. And multiplication means the number of times you add something over and over. What is 3 times 9 if not 3 plus 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 3? That is what 3 times 9 is. 9 threes added over and over. That's what 3 times 9 means. When would I add 3 9 times starting from 2? If I want to find the value of the 10th term, substituting 10 in here, 10 minus 1 is 9. Let's find the value of the 10th term. How many times do we add 3 starting from 2? 1, 2, 3, 4, 5, 6, 7, 8, 9. So to find the value of some imaginable term n, whatever n is, it could be 100. But whatever it is, you're going to add 3 one time less than the term you're looking for. If it's term 100 I'm looking for, I'm going to add 3 99 times. If it's 1000 that I'm looking for, I'm going to add 3 999 times. Why don't we add it 1000 times, Mr. Robinson? Because we are starting from the first term. If we're already at the first term, then if I'm going to add 3 even once, I'm now at the second term. Once is the second term. We're already at the first term. We don't have to add 3 at all to get to the first term. We're on it. How far away is the number 100 from the number 1? It's not 100 away. It's 99 away because we're already at 1, right? You don't say, well, let's see, 1, 2, 3. No, you say 2, 3, 4, 5. So that's what the n minus 1 is there for. You're adding 3 times n minus 1 means plus 3 plus 3 plus 3 n minus 1 times. Why do we do n minus 1? Because we're adding 3 over and over that many times. Why are we doing it one less time than the term we're looking for? Because we're starting on the first term to begin with. The first term's provided, and we only add 3 that certain number of times. So to find the 63rd term, we're going to add 362 times because we're already on the first term, and we're going to add 3 over and over. We get to multiply to make that work. And that's the logic behind it. I won't get deep into it. Hopefully that kind of made sense in it. That would be it. All right, so that's it for the Integrated Math 1, folk. Those are your questions. Thank you so much for asking the questions that you did, including things like the Batman question when we go back to school. Integrated Math 2 has 5 questions here, I do believe. That's it. So I'm just going to go ahead and start in, and if you clicked on the description section to get to Integrated Math 2, now you're here watching it. Beautiful. Let's take a look. Integrated Math 2, we're working on quadratic things now. We worked on polynomials in the past. Let's see what questions we got. I didn't really look at them. So let's take a look. All right. Why is it called a quadratic function when the highest degree of the equation is 2? Ooh, I'm curious because quad usually stands for 4. I mean, I have an answer. I don't know if it's the answer. I'm not like a head mathematician thing here. A lot of math terms and abbreviate, a lot of terms come from origins that were not English. They were Greek, they were Latin, they were Roman, things like that. Especially Latin. A lot of things are Latin. Just like people ask, why does M stand for slope? Because the M is somewhere in, honestly, I can't remember what the M is. The M is some Latin word that represents something that has to do with slope. I can't remember what it is. That's why slope starts with M. It's a Latin thing. Quadratic, and quadratic isn't a Latin word, but it's a word from some origin. I don't know what the Latin word is. It might be quadratus or something like that. There is a Latin word for square. Quadratus. I'm gonna say it's quadratus. That might be it. I think it is quadratus. Quadratus is Latin for square in English. We square terms when they're to the second power. Now that might be a different question. Mr. Robinson, why do we call this x squared? Mr. Robinson, why do we call this x cubed? Because in their physical occupied space, when we square something, when we multiply a square, like it's base times height, like this, base times height, the area here gives you square coverage, for something, because that's what happens in a square when you multiply something by itself. So quadratus being Latin for square, I don't know if it's actually quadratus. Quadratus being Latin for square, and squares being represented to indicate square coverage when we multiply two things, it gives you square. That's the reason. Now you bring up a good point. Quad usually stands for 4. So if quadratic functions are x squareds, if these are quadratics, and Mr. Robinson, if x cubes are cubics, by the way, why do we call these cubics here? Because in a cube is a bunch of six-faced squares. X times x times x gives you x cubed. That's in physical space. I couldn't do a quartic in physical space because it kind of breaks our laws of what we can perceive and do. If you want to look up something called tesseracts, that can give you the idea. It's going to be a little strange if you look at a looping animation of it. Mr. Robinson, what do we call an x to the 4th power thing if quadratic is used for square? There's another word that's very similar. Unfortunately, it is very similar sounding. You're just going to have to note the difference when you do it. It's not quadratic, it's quartic. Okay? And you've heard quarts before, like when you're measuring cups, 4 quarts in a gallon, things like that. 1/4. It's quartic. So I know what you mean. Quadricep, things like that, the 4 muscles, blah, 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 quad, all that. Hey, 4 sides. Now, by the way, why that other part? 4 sides, right? That's why quadratus square, that's why you do it. 4 sides to it. 4 sides. That's where your 4 can come from. The square comes from the idea of the square. Quadratic versus quartic. There it is. That was a great question, by the way, because that is something that can confuse people. Some people might think it's x to the 4th, whatever. In this case, it's not. All right, the power hour will extend beyond an hour here. I'm totally fine with that. Next question here. Can you show us how to graph a quadratic function? I know you show us all the time, but I'm still having trouble with it. All right, for me to do this one, I am definitely going to have to bring in graph paper. I should have prepped this beforehand. I'm going to, just give me a second. I'll talk about it out loud. Depends on what form you're talking about. I'm going to begin with, let me see if the other questions ask this actually. And I don't think I laid these ones out with formatting. My bad, guys. These should have had little lines to them. Opposite same, when you're graphing, what numbers do you multiply to get your points? Faster method. Okay, so this kind of talks about the same thing as well. If you're asking this question, maybe here I'll talk about non-vertex form. Here I'll talk about vertex form. Let me quickly check something before I bring up graph paper. I'm sorry, guys. This is a little unprepared here. All right. At some point in this video, I might do a quick pause because I have to get some more video space here. In fact, let me pause this video right now to get a graph. All right, the video's unpaused. I got graph axes right here. Okay, so the question, once again, is can you show us how to graph a quadratic function again? I know you show it all the time. I'm having trouble understanding it. Well, remember, you can always use a table. And I'm going to start with the idea of the table, specifically the parent function, f of x equals x squared. And let's construct the idea that when you plug in values for x, you get values out for y. F of x, same thing, x, y. Let's do some negatives, some positives, and 0. And when in doubt, use your damn parentheses. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. You hear me say this all the time. 1, 1, 2, 4, 1, 1, 2, 4, 3, 9, things like that. We use that concept. Negative 1 quantity squared is also 1. Negative 2 quantity squared is also 4. Negative 3 quantity squared is also 9. Parabolas have symmetry to them. Specific symmetry about the vertex such that you can reflect across said axis of symmetry. In this case, it's on the y-axis here. You can reflect across it, and you can get points that are corresponding in height the same distance away from the axis of symmetry, like so. This is the parent function, f of x equals x squared. Just like any other transformed function, you can always use a table if you want to plug it in. Just make sure you know your order of operations, use parentheses, and you're good to go. Now, you're probably asking, how do I do it without a table? It comes from the form of understanding the parent function 1, 1, 2, 4, 3, 9, because that is the behavior of quadratics in and of itself. So let's look at a new one. Let's look at g of x, and let's call it 2x squared. 2x squared. And this is kind of what we did in the notes as well. Now, 2x squared does the same thing as x squared. The difference is you multiply your x squareds by 2, and we do it in that specific order. You square x first. So you get these numbers first. This 1, 1, 2, 4, 3, 9 stuff, you get these numbers first, and then you double them. Times 2, all the way around, all these numbers get doubled right here. Okay, they all get doubled, and that gives you 18, 8, 2, still 0, and again 2, 8, and 18 because it's reflective, like that. Every point here, the origin is still here. Now you have 1, 2, 2, 8, 3, 18, which I can't fit, and negative 1, 2, negative 2, 8, like that, and negative 3, 18, which again I can't fit. And everything became twice as tall. And I want to say twice as tall and not like twice as skinny or anything like that. It's nothing to that realm. Everything became twice as tall because at the same x values, you are now displaced from your vertex twice as far as you previously were. What I mean is before we were up 1, now we're up 2. Before we were up 4, now we're up 8. You can see the numbers right here. 4 versus 8, 1 versus 2, 9 versus 18. Every distance has been doubled. That's why it's important to know your 1, 1, 2, 4, 3, 9 to say when I go 1 away, I go 1 up, 2 away, I go 4 up, 3 away, I go 9 up. From the vertex, by the way. 1 away, 2 away, 3 away. From vertex. That's why we state those things, because those are always used in quadratics. You always square your value first. You always square your value first, and then you multiply. This is a vertical stretch factor because it's stretched twice as tall here. Now, what if you do something that has a fraction? What if instead it's a 1/2? Let me erase some stuff I have. Let me get rid of the green as best as I'm able. What if I have a fraction? Let's do 1/2 in this case here. Sorry about this. Let's do not x squared, but 1/2 x squared. Let's do g of x equals 1/2 x squared. Same thing, only now you divide by 2. Multiply by 1/2, divide by 2. You square it first, take half of it. 0 times 1/2 is 0. 1 times 1/2 is 1. Half of 4 is 2. Half of 9 is 9 halves. It's 4.5. I'll put 4.5. Okay. And same thing on the other side, right? We'll just reflect after if you want to. Still at the origin, vertex 0, 0, or up 1/2, over 2, up 2, over 3, up 4.5, like so. Now, and I reflect here, now your distances, your heights, excuse me, are halved from what they previously were before. They are now halved. Everything is half the height because that's what the vertical stretch factor tells you to do, and you keep going. I could keep going here, by the way. If 4 squared is 16, guys, then half of 16 is 8. That means we're at 4, 8 right here. I can even fit another point here that I ordinarily wouldn't have been able to fit. So there's even another point for you guys. Now, I don't use a table. I'm using a table to make sense of what's happening here, but I don't use a table when I'm doing this because what I say is, remember 1, 1, 2, 4, 3, 9. You don't have to remember it. Just remember behavior quadratics. What's 1 squared, what's 2 squared, what's 3 squared. Understand that that occurs first when you're doing quadratics, and then you multiply by your number after. Sometimes you divide, you take half, or you double it, or you triple it, and it's only applied to the vertical component. Only the vertical component is manipulated. You go over 1 in x. You go up 1 times whatever it is after that. 1 times 1/2, 1 times 4, whatever it is, and it's applied thereafter. And that's how the vertical stretch factor is applied. That's how we graph a quadratic function again. Now, one more thing. If this is a negative, let's just erase all this. If this is, say, negative x squared, just going to jump to that. Then we'll do, if you want to see more on this question, check out the last question that's being asked. That way you can do some vertex form stuff. Actually, that would have been answered a little more on the next question, on the bottom question here. Why don't I keep going on this one? If you're the bottom question person and you see your question, I'm going to say refer to this question up above. If that's okay. By the way, I'm going to have to find a way to make some room on my computer here in a moment. If this is negative, guys, negative means your things flip over. -9, -4, -1, -0, -1, -4, -9. So now everything flips over. Hey, 1, 1, you go down. 2, 4, you go down. 3, 9, you go down, etc. Flip it over. So anything that's negative, I still apply my 1, 1, 2, 4, 3, 9, but I flip it over. If it's a -2, I double my heights downward. So -2, I go 1, 2, 2, 8, 3, 18. Take your 1, 4, and 9, and you double them, and you go that much further down. All right, now, what if we are displaced from the origin with our vertex? This is where things they don't get tricky. This is where you just have to take into account how the shift does things for us, right? It helps us out in and of itself. And all you got to remember now is the 1, 1, 2, 4, 3, 9. I'm actually going to go completely tableless here on out. You can use a table to confirm bits, but I want you to make sense of the fact that when I look at the point 5, 5, I'm not really using that. I'm not really thinking of 5, 5 when I do something. What am I talking about? Well, let's check it out. What if I have something like f of x, g of x, doesn't matter. What if I have like f of x equals x minus 4 quantity squared plus 1? Okay, like this. How do I graph this? Well, vertex form, I'm not going to talk big on vertex form. Vertex form is opposite, same right here. So vertex here is 4, 1. 4, 1, boom. So I plot the point right there. All right. Everything I do now is from the vertex. What I mean is every distance I displace from the vertex will be counted. I'm almost treating my vertex as my origin. The fact that this is 0, 0 does not apply to me in the least. I'm not even really looking at it when I'm doing anything. My idea of everything I do now is displacement from vertex. It's displacement from vertex. What I mean is, and this is it. This stretch factor is 1. You don't see it. That means it's a 1. Like the parent function, it's 1, 1, 2, 4, 3, 9. That means from my vertex, just like from the origin, but from my vertex, I will go 1, 1. Whoa, I not want to draw. I go 1, 1, 2, 4, 3, 9. And you reflect across your axis of symmetry, like over here and over here. I'll draw the axis of symmetry later. I'm just kind of getting some quick ones in here. So there is that graph. 1, 1, 2, 4, 3, 9 is from the vertex. Some people might ask, Mr. Robinson, how did you get the point? What's this one right here? Mr. Robinson, how did you get the point 3, 2? I didn't get the point 3, 2. I went over 1 and up 1 squared. I went over 2 and up 2 squared, and over 3 and up 3 squared. I didn't get 3, 2. I didn't see this as a 3. I saw it as 1 to the left. I saw it more so as -1. I did this. I saw -1, 1. So when you ask Mr. Robinson, how'd you get 3, 2? I didn't. Everything's based on the vertex. Everything's based on the vertex right there. And that's that tableless format. There's more that I'd want to say that comes into, I'll show you just in this one. If I plug in 3 into here, I get 3 minus 4, boom, plus 1, all that mamma jamma equals. 3 minus 4 is -1. See, this is the number that you square. See, you don't square the number 3. Even if I'm plugging 3 in for x, I'm not squaring the number 3. I am squaring the -1, my distance to the left. And then I got a plus 1. -1 squared is +1. This 1 is how much I'm going up from this 1 right here, my vertex value. My vertex value. I'm going up 1 from this 1. That's where I'm getting my 2. But that's if you use a table. I'm not. But that's still the idea that you can do, and that's where those numbers come into play. I'm not squaring 3 when I plug in 3 into there, because vertex form considers my vertex with that. I'll do one more, then I'm going to move on here. Let's do a fraction. Let's do an upside down fraction, make it a little more complex. Let's cover this in greater detail. Here we go. Let's do g of x equals, let's do -1/3 times the quantity x plus 1 quantity squared plus 9. So I can get this nice and big here. -1/3 x plus 1 quantity squared plus 9. My vertex is at -1, 9. It's the opposite same bit right there. So I start right here. Everything I do is going to be based on this. Because it's negative, I'll be going down instead of up. So even if I said 1, 1, 2, 4, 3, 9, guys, I'd be saying 1, 1, 2, 4, 3, 9. Just ignore the negative here on out. I'm going down. Now, instead of 1, 1, I'm going to go a third of 1, and a third of 1 is 1/3. You divide your numbers by 3. 1/3 of 1, boom, is 1/3 down from vertex right there. If I go over 2, I'd be doing 2, 4, but now I got to divide 4 by 3, right? Take a third of 4. So this is applying that stretch factor now. A third of 4 is 4/3. You might not know what that is. Maybe you skip it. Right? Maybe there are fractions that are improper, that are weird, you don't have a calculator you can't use. Okay, skip that one. There are a lot more points we can choose. Specifically, some of these odd numbers here. Not all of them. If I go over 2, down 4/3. Oh, I don't know where that is. Let's keep going. If I go over 3, 3, 9, right? 3, 9, 3, 9. Not 9. What's a third of 9? Divide by 3. It's 3. 9 divided by 3 is 3. I go over 3, I go down 3. Remember, instead of 3, 9, I'm going down 3, a third of 9, a third of 9, okay? That was a good point to choose. 4, 16, what's 16 divided by 3? Not a great number. I know what it is, but it's not a great number. If it's not an integer, I'm going to move on for now. 5, 25. How'd you get 25? It's 5 squared. 5 squared. 525. What's a third of 25? Divide that by 3. Oh, you can't. You can, but it's not an integer. Skip 5. 1, 2, 3, 4, 5, 6. 636. 636. 6 squared. 36 divided by 3. Ooh, that works. That's 12. We go down 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's a point. I feel like no other points I'm going to find I can divide by 3 and fit on this graph. So these are good points I can fit on the graph there. How does the axis of symmetry work? Because you might want to draw one every so often, not even just for me, but for yourself. Right? You might want to draw one that's like, oh, sorry, I'm changing color here. Oh, I need one to be able to see what I'm reflecting across. Here's my vertex. All parabolas are symmetrical, so we're going to reflect across this vertex with corresponding heights the same distance away from the axis of symmetry, like so. 1 away, 3 away, 3 away, 6 away, boom, and then 1, 2, 3, 4, 5, 6 away right there. So there's that symmetry, and we plot 4, 5, 6. 4, 5, 6. Okay, I think that's right. So I could draw the graph there with the waterfall effect. Not too beautiful. Oh, it's not bad. I get that one there, and I get that one. That's pretty good. And there's the graph. Now, you could put the other points if you felt like you knew what to do with them. 4/3, by the way, is 1 1/3. I was close. 16/3 is 5 1/3. So 1, 2, 3, 4, 5 1/3. That one's pretty good right there, by the way, if I reflect it. There's my 5 1/3. Here's my 4/3. That one's not that close, I guess. I should have done it more like that. 25/3 is 8 1/3. So 5 1/3, 6, 7, 8 1/3. It probably should have been more right here. And 8 1/3. There we go. Looks like that. So anyway, those are the other points. If you did find them dividing by 3, it continuously goes down. It's not a constant slope. It is increasing more as we go down. There's the ideas. So you find the vertex. Treat it as your new origin. Know your 1, 1, 2, 4, 3, 9. It's the behavior of quadratics. Your values get squared. Your x values, not your x values, but your displacement from vertex 1, 2, and 3, they get squared. And then we multiply by stretch factor. That comes after you square it. 1, 1, 2, 4, 3, 9. Double it. Take a third of it. Flip it over. That's the behavior there. I hope that covers it. Because I'm well beyond my power hour here. Probably running. So let me check my memory once again, because I know I'm running low. 7 gigabytes. I can probably do this. Let's check it out. All right, the next question. How do you determine the axis of symmetry? Oh, good question. We're talking about this. How do you determine the axis of symmetry? Well, this one, I don't know if you're asking how do you know where to draw it, or how do you write the equation. How do you draw it? It's always for parabola. So axis of symmetry only exists for some certain kinds of graphs. Parabolas, they have them. Absolute values have them, because there is symmetry in them. They always will. There's not a time where they won't. Otherwise, they're not parabolas, or they're not absolute values. Axis of symmetry is a vertical line that goes through your vertex point of your thing. So I always know to draw it vertically through the vertex. If you're asking that question, that's the answer. If you're asking how do you write the equation of the axis of symmetry, it's pretty straightforward here. It's always an x equals equation. This one happens to be x equals -1. That is your, I don't know if you can really see that. Let me use a different color. This axis of symmetry here is x equals -1. That's your AOS, axis of symmetry right there. All vertical lines are x equals equations. They're not function equations, so it's no f of x or y equals thing. There's no y equals mx plus b we can do for this. This is a vertical undefined slope. They are x equals equations. Mr. Robinson, x goes left and right. Why is this an x equals equation? And furthermore, why are y equals equations horizontal? This is left and right. We determined which x value we landed on. Here's x equals 0. Here's x equals -1, -2. See how I'm going left to figure these out? -3, -4, -5, -6, -7. The up and down portion is describing, these are all of the points where we get -1 for x. Can someone tell me what this point is? It's -1, 0. Can someone tell me what this point is? It's -1, 5. Can someone tell me what this point is? It's -1, -4. What do all these points have in common? X equals -1. So that's why these are, the vertical lines are x equals. Y equals is for the same reason. We go up or down to find the y value, and it expands across that y value fully because those are all the points where y is that number. This would be for y equals 2, very poorly drawn, because y is always 2 here. Here's 2, 2, here's 6, 2, here's 10, 2, here's -1, 2, right? Those are all the times when y is 2. How would you know without the graph where the axis of symmetry is drawn? Well, vertex form can help reveal that pretty fast. If you guys know that vertex form has this appearance each time, boom, like that, your vertex always appears at, your vertex is at h comma k. Your axis of symmetry always appears at x equals h. Whatever h is in that opposite same format, whatever h is, x is that same thing. See here, h was -1. What was the axis of symmetry? X equals -1. You could just look at the vertex form and go, hey, if this is my vertex, that is also the line because it goes through the same x as your vertex, right? It's vertical through your x. So hopefully that covers that pretty well there, just with that one example. And, you know, I'm not going to do multiple examples. You find out what h is based on your vertex form, or you draw the graph, cut it through, and it's the vertical line that hits through whatever x value it does. It's an x equals equation. There it is. Okay, next question. Why is it opposite same, and why can't you distribute before the thing by the power? Okay, first of all, these are two different questions, and I'm going to treat them as two different questions. I'll do the second question next, and the thing before the power, I think you mean the stretch factor, the a. And don't worry, I'm not laughing at you. It's just funny when people are like, nah, I don't know the word. Tell me, help me out here. But they are two different questions. First question here, why is it opposite same? They're referring to the vertex. Okay, when we look at this equation, and this is a good question. I could get deep on this. I don't know how much time I have to get deep on it here. I could get deep on this here. They're asking why is this opposite same? Let's break it down by the understanding that the vertex does have to do with hk, where h associates with your x value and k associates with your y value. Here's the thing. I'm going to transform this equation in two different ways. First thing, I'm going to turn f of x into y. I'm going to make it look like y so you really understand what I mean when I call this thing y. I'm going to write y equals a times the quantity, x minus h squared plus k. Next thing I'm going to do, you might notice that if x associates with h, it's kind of nice that they happen to actually have x and h on the same side of the equation together. Heck, they're in parentheses together. And notice that y and k are on different sides of the equation right now. Anyone ever notice that? If x associates with h is on the same side, y associates with k, it's on the other side. What if we put k on the same side as y? What if you move it over? How would you do that? You would subtract k from both sides. So you'd get y minus k equals a times x minus h quantity squared. Does this look very opposite same anymore? No, now it kind of looks opposite. Heck, I'll wrap this around parentheses just to kind of give it that look. This looks opposite. Your vertex, even if it was written like this, is in hk. It's opposite. Kind of weird, huh? So why is it opposite same? Because k is on the wrong side of the equation for this when this is happening. Now, when I transform it, you can probably see that. So that answers that. Someone else might ask, so I can just cover this now, why is it opposite to begin with? That's kind of a different question here that I want to try and answer. And by the way, that's not to your next question just yet. Why is it opposite to begin with? Well, let me talk. So let's get back to the idea of vertex. We're going to go back to the original one right here, if you guys are fine with this. Oh, also, you also might ask, so why do we write it in this form instead of the other form where it's like that? Because in function notation, the function kind of stays on its own side of the thing. Oftentimes, we get y by plugging in for x. We wouldn't want it in that way to make it look like that. We like y equals dependent variable by itself. So that's why we put it on this side. Hopefully you're okay with that for this function. Okay, why is it opposite to begin with? Remember that this represents vertex, okay? I'm answering your question when I say this. Vertex is either always the bottommost point of your graph or the topmost point of your graph. It's an extreme. For now, let's just pretend like it's bottom. Let's pretend like A is positive. It's going to be a bottommost point. Why is it the bottommost point? Why does the bottommost point occur at hk? Well, let's talk about the idea that x is an independent variable. Let's substitute h for x. Let's substitute h for x. What do we get? So f of h is going to be a times h minus h quantity squared plus k. H minus h is 0, and 0 squared is 0, and 0 times a is 0, okay, and 0 plus k equals k. You know what f of h is? It's k. When you plug in h for x, you get out k for y. So that's the first bit. When you plug in the value that's equivalent to the number that's being subtracted in your... Hey, also, I want to let you know my computer stopped recording on me. I do have to answer these last ones fast, I guess. Actually, this is the last question. These are the last kind of questions here. So, sorry if you missed something here. What I last said was h. You plug in h for x, you get out k for y. So there are kind of two ways that I can answer what we're talking about here. I think part of what I'm answering is why is this the vertex? I guess what I was starting to answer. You're asking why it's opposite, but why it's the vertex also answers this. When you plug in h, you get k. Remember, we plug it in for x, and h happens to be the other thing that's a parameter within your equation already. But if you plug in that number here. Now, why is that a vertex? Why does the vertex bottom out when we do that? Well, because keep in mind, guys, when you square a number, it becomes positive, right? If I asked you, what number could I plug in that when I square it, I get the lowest, the smallest result I possibly can? What number can I plug in here so that when I square it, it becomes the smallest possible result? You might think, oh, negative 1,000. If you do a really small number like this, when you square it, guess what that becomes? Positive 1,000,000. That number's huge. Plug in positive numbers, you square it, it's positive. Negative numbers, you square it, it's positive. The smallest result you can get out here is 0. How do you get it? I'm hiccuping. How do you get it? By squaring 0. How do you get 0 in this quantity? How do you get 0 in this quantity here? You gotta make x be the same thing as h. Your x value has to be the same thing as h. Why am I talking about getting the smallest value out? Because that's what's going to minimize this whole ordeal that's in here. That's going to minimize your y value. It's going to give you your lowest point. If you want to get the lowest point out, you want it so that when you square your number, it becomes as small as possible, right? If y becomes everything that's calculated here, you want this to become as small as possible. So you want your difference in here. This goes above and beyond what a lot of people are asking here. You want it to be as low as possible, or as small as possible, so that y becomes as low as possible. Why is y sometimes the highest point? Why does it change this way? Because now when you multiply this by a negative, it becomes the highest point, because every other number becomes more negative as a result of that when it's negative there. Okay, so now to the question as to why is it opposite? Because what you're doing here when you're plugging in numbers, remember that when you plug in h for x, like here, let's use the actual equation. When you do like 2 times x minus 3 quantity squared plus 1, when you plug in 3 for x, what you're actually doing is, see, the opposite thing right here is not about really this. It's really about what you're plugging for x. It's saying, what do I plug in for x to minimize my value to get my vertex? That's why I had to talk about vertex first. When I plug in 3, my distance from my vertex is 0 because I'm on my vertex. Excuse me. So why is it opposite? What you're doing when you're plugging numbers in for x here, you are finding your distance from your vertex. That's why. So remember, so look, if I graph this, I'm going to graph it super fast. Opposite, same, 1, 2, 2, 8, da, 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 some stuff like this, right? You graph it. I'm not even going to connect the dots. Yes, I am, because I'm like that. Okay, vertex is right here. When I go over 1 from the vertex, my x value itself is at 4. I plug in 4 into this equation for x. Why do I subtract 3 here? because that is saying my distance from my vertex. 4 minus 3 is 1. 1 is the distance from the vertex. So why is it opposite? So you can calculate distance from vertex. But really, why is it opposite? Because we're not actually talking about this number here. We're actually talking about this number here. This number, when it's 3, minimizes my value here, so it lowers, it makes my point as small as possible, which gives me my vertex. I know those aren't things that's going to help you with your math. Probably. But it does make this, give it a completist idea, and it does show why using a table becomes a little bit moot in these ordinary ideas when you do that. So I answered a lot of questions with that. The very last question, because I did run out of computer room, and I'm redoing this as like a second part. Oh, this. So by the way, well, actually, I'll get to that. Why can't you distribute before the thing by the power? Let's see how much time I gotta keep checking my memory here. Okay, not much time. Why do you distribute by the thing before the power? I don't need this anymore. Why don't you do it? So, okay, same equation I just had last time. F of x equals 2 times the quantity x minus 3 squared plus 1. Why can't I do 2 times x, 2 times negative 3 before I square it? So why can't I make this be this and then square it and do something here? Well, first of all, I don't know why you'd want to do that. Oh, I guess when you plug in a number, right? When you plug in a number. But anyway, why can't you do this anyway? I don't know why you'd want to because it's not in vertex form. But you can't because it breaks order of operations. Mr. Robinson, why do order of operations matter? To reduce ambiguity in math. We want to not know that we'll get different answers. Different people will get different answers and have them all be accepted because it wouldn't be a function otherwise. So we state that exponents go before multiplication because they wanted to. But there's a little more to it than just that because exponentiation means how many times you multiply by something. So check this out. I'm curious if you guys know this. X minus 3 squared means x minus 3 times x minus 3. I know you know that. Did you know that when you distribute this 2, you actually cannot distribute into all 4 things like this? You actually only distribute into one quantity like this? You're like, BS, Mr. Robinson. Really? What? Are you sure? Yeah, I'm sure. Check this out. Guys, what's 2 times 3 times 4? 2 times 3 is 6. 6 times 4 is 24. Okay. Should I distribute the 2 into the 3 and the 4 and make that 6 times 8 and make it 48? No. You only, when you did 2 times 3 times 4, you said 2 times 3 is this, and that result times 4 is that. You didn't distribute it into here. You only multiplied once. All multiplication. This is all multiplication. This is 2 times this times this. They all multiply just once. The distribution goes into the terms within the quantity, but you only distribute once here. So to go back to the idea of why we don't do that, why we don't distribute first before you square it, because now you're going under the impression that you distribute the 2 into the x minus 3 to make 2x minus 6, and when you square it, that means it's 2x minus 6 times 2x minus 6. This shouldn't be our result of multiplying this through distribution right here. This one, when we distribute, if I decided to distribute this first, that would be 2x minus 6 times x minus 3. See, these are not the same here. These are not the same. This one is wrong because you distributed first under the impression that the 2 can distribute into both sets of quantities that are multiplying together. You can't do that. This is another way that shows that right here. So you can't do it because it breaks order of operation. We have order of operations to reduce ambiguity in our math. Otherwise, there'd be multiple correct answers for the same kind of math thing. And it shows that when you use the exponentiation to expand right here, distribution does not apply. We saw it with real numbers, and we noticed that if we do distribute and expand, it becomes a different result of what is there. Okay, so that's all the questions there. And the final question here, which I already answered to the person who asked this, when you're graphing a quadratic function, what numbers do you multiply to get your points, the faster method you taught us? I answered that right here. So if you can find this question in the timestamp to find your thing, that'll help alleviate that for you. Can you show us how to graph a quadratic function again? I know you show us all the time. I'm still having trouble with it. So hopefully that alleviates that for you guys. I know this is longer than an hour for the Power Hour, but this covers things for both my Math 2 and Math 1 bits. So you're going to see this video, probably upload Saturday, what have you. But that'll do it for you, this year, guys. Thank you guys for watching the Q&A Power Hour, and I will see you in 2 weeks for another Q&A Power Hour video. Bye.